Now let's look at running water, or stream flow as they say. Streams, rivers, brooks, canals, anything where water runs. There's obviously oceans and lakes and seas and glaciers where the water kind of stays still, and then you have streams where water runs, and they run essentially because of gravity. Water falls near in a higher elevation, and the waters collect because all the droplets, as they're going down the hill, they collect and they form one big stream, and then that eventually carves out a little path for itself to run, and eventually when that gets big enough, you have a river or a stream or a brook or whatever you call it. A stream's speed is influenced by size, shape, and roughness. The larger and smoother it is, the larger, in other words, the more water it is, the heavier and the more momentum it builds up, and so the faster it runs. Also, the smoother it is, the faster it runs because there's less resistance. Laminar flow is something that describes the fact that the water particles go parallel to each other and they don't necessarily mix, which is very common in moving streams. If you have a regular, flat, plain stream, the water molecules that enter the river, they run down next to each other and they don't actually mix with each other because they're both running towards the lower elevation. They're both running in the same basic directions. But you also have streams that have turbulent flow, which is the opposite of laminar flow. Turbulent flow means there's swirling motions with rivers that have curves that go around. In that case, of course, you do have mixtures between the various waters in the stream. The gradient means the slope of the stream. Obviously, the steeper the gradient, the faster it's going to go. The greater the stream flow, because gravity is going to cause it to go faster if it's on a steeper hill. But of course, generally speaking, streams and brooks go from uphill to downhill, from the top to the bottom. Of course, they could flatten out, and they very often do flatten out for a while, but overall, the axis, there's no such thing as a stream that flows uphill for its entire run. It has to basically flow downhill. Maybe you'll have a few little uphills. You know, if you have a stream over here and it goes like this, maybe it'll go a little like this and then go back down. But overall, you cannot have a stream that runs from here to here. That doesn't make any sense. The stream would have to run downhill. Discharge means the volume of water flowing in the stream. Expressed in cubic feet per second, that's the measurement, but essentially what that means is how much water the stream actually has going through it. As stream discharge increases velocity as it discharge increases, in other words, as the amount of water increases, it's heavier, gets more momentum, therefore velocity, which means speed, the width, and the depth of the stream also increase, and that, of course, is common sense. How do you calculate the gradient? How do you calculate the stream's slope? Well, it's the same way you would any type of a hill's gradient. Gradient just means slope. Just divide the drop by the distance, just like any other hill. If a hill goes down a mile, if a hill goes a mile and it goes down 30 feet, well then it goes down 30 feet for every mile. If it goes up 30 feet per mile, then 30 feet in a mile, well then of course it goes up 30 feet per mile. When people are hiking in mountains, they want to say, well, this mountain is so steep, it gains 100 feet per mile. What they mean is that every mile they hike, they're going up another 100 feet. An example, a very simple example, you may see a question like this on an exam. A stream begins at 400 meters sea level and flows a distance of 1,000 kilometers to the ocean. Now, the ocean, of course, is at zero by definition. An ocean is at sea level because, well, that's why they call it sea level, because that's the level of the oceans and seas. So if it went from 400 to 0 in 1,000 kilometers, that means the average gradient is 0.4 meters per kilometer. Just divide 400 by 1,000. 400 divided by 1,000 is 0.4. You can figure it out in your head, or you can just use a calculator. And so the average gradient for this entire stream is 0.4 meters for every kilometer. The base level is the lowest elevation at which a stream can erode its channel. In other words, that is the lowest level at which this particular stream can exist. It may vary from stream to stream. It may depend on how steep the rest of the river is, and may depend on how much water there is, how much resistance there is. But the lowest is obviously when you get to a certain point, as it goes down, down, down. At a certain point, it's just not going to have enough momentum anymore to flow, and it's just kind of going to stop or end in a lake or something. Or the ultimate base level is sea level. That's the lowest point in which erosion could lower the land, because at that point there's no more gravity. You're at the lowest point. You're at sea level, and so the stream by definition is going to flatten out and eventually stop flowing. When sea level falls and the land rises, of course there's a lower ultimate base level, because again there's just less gradient. There's just less steepness. And there also could be local base levels, including lakes, resistant rocks, mainstream. What that means is that when streams in this area run into a lake, obviously they're going to stop flowing. Now let's discuss more about water and shorelines. And stabilizing shorelines. Shorelines, of course, are the sides of the river, and that's something that very often people want to do because you want to build houses or structures on the banks of the river, and you don't want them to be washed away as part of the river. So you want to be able to stabilize the shoreline of the river or the lake or whatever it is. You can build structures to protect the coast from erosion, like groins, which are barriers built to strap the sand that's moving parallel to the shore. In other words, you build a wall of sand to prevent the water from eroding whatever is on the shore itself. You can also build seawalls and breakwaters, which are again both different types of things that stop the water, stop the river from moving on and eroding the shore, the land that's underneath the shore. You can also do what's called beach nourishment, which means you add sand and you add other materials to beaches so that the beaches don't get washed away. Eventually, the river beach might get washed away, and then the water will get wider, and the river will eventually erode the land. So what you can do is you can add sand and other materials to the beach, and therefore prevent it from being washed away. You can also relocate buildings. I guess that's not really that's not really stabilizing the shoreline. That's just kind of running away from the shoreline. You're saying, okay, well, we were worried that the water is going to wash away the land underneath these buildings, so we'll just move the building. Urbanization causes shoreline erosion because it makes the soil less stable. What people do is they dig out the soil and they build concrete on it, and they build all sorts of things on it, and that decrease of the natural barriers in beach areas tends to cause shoreline to erode. So that's why people very often have to build these breakfronts or build other things that prevent erosion. If you live in Coney Island, or if you live in the Jersey Shore, or you live next to the Mississippi River, or whatever it is, very often these cities have to take steps to make sure that their land doesn't get eroded, because then the houses would wash away, and you don't want that to happen. So development in coastal areas has caused an increase in efforts to stabilize shores, because they don't want their cities to be washed away. And of course, an increase in the value of shorefront buildings has increased the efforts to protect from storm waves. People like to live and have shopping places and have entertainment on the shoreline because it's pleasant and it's comfortable and it looks nice, and it's also a little bit more moderate in terms of temperature, and so therefore that's one reason why stabilizing shorelines has become so important. Groundwater, and I discussed this a little bit before, but groundwater is really the idea, basically the same idea as well water. Groundwater is the largest freshwater reservoir for humans. In other words, that's how most people actually get their water. There's also water in lakes and reservoirs, but groundwater is underneath the ground, and this is the water that's not held as soil as the moisture percolates downwards until it reaches the layer where it cannot penetrate any further. If you picture there's mud in the ground, but then if you go further and further down, or soil in the ground, and you go further and further down, eventually you're going to hit a hard rock. And the water, as it seeps down, the stuff that's not absorbed by the plants or absorbed by the soil, is going to eventually hit this rock, and that is called the water table. This limit is called the water table. That's where all the water sits. Then you have above the water table, you have the unsaturated zone. Saturated means it's filled with water. So the soil that's not filled with water, in other words, the soil above the water table is not fully saturated, but the soil right above the hard rock is fully saturated. You also have caves or caverns, which are formed by dissolving rock underneath the Earth's surface, and they are commonly formed from limestone. Most features on Earth are dug out by water at one point or another, so you can see a picture over here of Carlsbad Caverns, which is an example of a cave or a cavern that was formed by dissolving rock, which of course was done by water. Another type of surface water is a geyser. This is a picture of Old Faithful Geyser in Yellowstone Park in Wyoming. And you can see it's in the middle of the winter because you can see the snow all over the place, and yet there's a very hot cloud of condensation of steam, or not really steam, but water vapor that is rising because geysers are hot springs of water that exist beneath the ground and that shoot upwards and release the warm water above the ground. It's a form of groundwater. It's a hot spring in which water erratically boils, sending a tall column of steam, steam over here, into the water and into the air. Into the air above it. Old Faithful, of course, is called Old Faithful because it's not really so erratic. It happens pretty consistently, but I guess most geysers are kind of erratic and unpredictable. And the way geysers erupt is the pressure under the ground that's keeping the water where it is decreases at random intervals, and the water boils suddenly, and a plume, which means a column of hot water, steams up into the air, such as in the example that you see here in the picture. Alright, so groundwater is the issue. Again, a geyser is not really a form of groundwater. The groundwater is the water on the water table that we dig out with wells. The problems with groundwater, or at least the challenges that are faced when you're dealing with groundwater, first of all, it says over here it's non-renewable, but I don't know if I agree with that. I guess if you keep taking the water and using it for other things, eventually it might fall in the ocean, or the rain that comes from the evaporation. I don't even really agree with that, so never mind. I'm just gonna delete that. Sorry. The groundwater could become contaminated, where that's obviously you could have pollution. You could have well water could become contaminated if chemical companies leak chemicals into the soil, into the water table. That could be a problem. Pollution could cause contamination. It comes from sewage because of broken or inadequate sewage or septic systems. Waste from farm waste or septic tanks. One way to take care of that is that slightly clay sand, which means sand that has very, very small particles, that's why it's called clay, can be used to naturally remove sewage pollutants from a stream. If you run these tiny little sand particles or clay particles through them, they can actually kind of cleanse out the pollutants and particles. Also, other things can cause problems. Highway salt, fertilizers, these are all things that can seep into the water table and make the water table not as pure as we would like it to be if we're going to drink it. Now we have two more agents of erosion that we are going to discuss, glaciers and wind. We'll also discuss deserts. Desert is not really an agent of erosion, but glacier is a way that rocks and sand, remember, erosion just means rocks and sand particles and things like that get moved from place to place. And wind also moves things from place to place. So let's look at glaciers first. We discussed glaciers before. I showed you my pictures of Byron Glacier. One of them I got from Google Images. The other one I actually took with my own camera when I was there. Anyway, so a glacier is a thick mass of ice that forms over land from the compaction and recrystallization of snow and shows evidence of past or present flow. In other words, like I said before, you have rain or snow that falls in a particular area. It gets heavier and heavier because more and more snow falls on top of it, and it freezes, and it becomes ice. Look, you've all seen when you have snow, at first it's nice and fluffy. After a while, after a few days, especially if there's more snow and you dig to the bottom, or if it just sits there, it's going to become harder and harder because it's going to keep getting compacted and compacted by gravity. And so eventually, if it's big enough, it becomes a glacier. The more snow falls on top of one area, it has to expand because there's no room for it to keep growing. So because of gravity, it spreads out and spreads out and spreads out, and it becomes a glacier. You could have a valley glacier, which is also known as an alpine glacier, which they form in mountainous areas, and the glacier itself spreads in the valley between the mountains. Byron Glacier is an example of a valley glacier. You can see I just refocused the screen over here. This is back to our picture of Byron Glacier. You can see that it's a valley glacier because it forms in the mountains. Probably a lot of snow falls up here, but it naturally moves, it naturally expands towards the valley in between two mountains. And of course that's only natural because of gravity. When you have got a lot of snow, and if the snow all falls over here and causes it to expand and expand and expand, it's going to expand naturally downwards towards the valley. It's not going to naturally expand upwards towards the mountain slopes over here. This area, which I think also might be Glacier, also might be Byron Glacier, in a period of time that is more maybe more wintry. But also you can see it's the same idea, where the whole mountaintop is covered with snow, but it also, the glacier expands through this valley over here. Many different types of glaciers are valley glaciers. You have ice sheets or continental glaciers, which are very big glaciers that form across an entire continent or an entire area of land. Those are large-scale glaciers, like Greenland and Antarctica, two areas that are basically covered by glaciers all year round, or mostly covered by glaciers all year round. You have the ice caps, which are, of course, are at the poles, at the North Pole and the South Pole. Those are also types of glaciers that remain frozen, although obviously a lot more of it is frozen in the winter than in the summer. And you have piedmonts. Piedmonts are a very interesting little phenomenon. Piedmonts are when you have big glaciers that kind of have little fingers flow out from them. I mean, I'll show you a picture of a Piedmont glacier over here. This is a Piedmont over here. You can see the big glacier in the background, all this ice over here, and I guess it was trying to expand, and there was no room to expand because of these rocks over here. So it expands in a little finger that comes all the way out here, kind of like a little tendril, like the Finger Lakes in upstate New York. Well, those are water, but where like a little tendril that comes out from the glacier to form its own little mini glacier at the end. And glaciers, glaciers don't really move per se. What they do is they expand. A glacier has a zone of accumulation, which is where the glacier forms, which means the center part of the glacier where all the snow falls, the glacier where all the ice forms. Then you have the zone of wastage. That's all the way usually at the very end of the glacier, at the southern part of the glacier, or at the part of the glacier that's a little warmer, where the glacier tends to melt. The difference between the big glacier that we saw in the winter at Byron Glacier and the smaller glacier in the fall or the summer is that the one that was smaller just had most of its wastage zone melted, whereas the one in the winter had most of its wastage zone frozen. And the glacial budget, I call everything a budget in earth science, is the balance or lack of balance between the accumulation in the upper end and the loss at the lower end. Obviously, if you have more and more snow and ice accumulating at the top and causing the glacier to expand than you do that's melting at the bottom, well, then you're going to have the glacier expand. If you have more melting at the bottom than you have accumulation at the top, you're going to have the glacier get smaller. Again, that sounds pretty obvious, but let's look at it. If accumulation exceeds the waste, then the glacial front keeps advancing until the two factors balance. When the glacier is big enough, when you have a Piedmont like this, you have the glacier, and the accumulation zone is probably all the way back here, somewhere in these mountaintops. And this is the zone of wastage, because this is when it starts melting, the first thing that's going to disappear is this part over here. But if it's winter and there's more stuff accumulating back here and causing the glacier to expand, this is going to come further out. So where it ends, that's the zone of balance. If in the winter, obviously, it's going to be much further down here. In the summer, it's going to be much further up. But either way, that's the quote-unquote glacial budget. Eventually, when the accumulation and wastage are balanced, then the terminus, which means the end, is stationary. And that's obviously common sense. Whenever it reaches that balance, it stays there. And of course, it can happen and change over a long period of time. What do glaciers actually do? You can see a nice little picture of the Matterhorn, very, very steep mountain in the Swiss Alps. You have glacial troughs, which is a V-shaped valley that's widened and deepened by the glacier to form a U-shape. What happens is if you have a valley, valleys will generally start off as V-shaped, and the reason why they'll start off as V-shaped, and I got a couple of great pictures that I'll show you. I'll show you in a couple of minutes to illustrate the difference. But the V-shaped, most valleys are going to start off as V-shaped because they're going to be cut out by flowing water. The flowing water is going to make the land in the mountain get lower and lower and lower because the stream is digging out more and more land until you have kind of like it just sinks the land where the river is going all the way down until the valley is kind of shaped like a V. But a glacier, which pounds through it with a tremendous force of ice, expanding and breaking everything out of its way. Ice is very powerful like that. Can cause the valley to be dug out to become more like a U. A hanging valley is after the ice recedes. In other words, after the ice melts, the valleys are left standing. And rivers flow through these valleys to produce waterfalls and steep rapids. You can imagine all the deformity that's caused by glaciers and what happens when when the glaciers do melt. You can have all these strange landforms that were dug by the glaciers that the rivers can now cause very strange occurrences like waterfalls and whatnot. Horns are like sharp pyramid-like peaks in mountains like the Matterhorn. A fjord is a deep, steep-sided inlet in the sea. I'll show you a picture of that also in a moment. But let's first look at the U-shaped valley and the V-shaped valley. Here, this is an example of a V-shaped valley, and you can see this is obviously there's no glacier here, there's no ice here. This is just a regular valley. And you can see how probably at one point was one big mountain, and the stream, which is down here, you can see the river down here, might have dug big holes, dug a big path through the valley. And that caused the valley to be more V-shaped, where you have steep slope on this side and a steep slope on that side. On the other hand, look at a glacial valley. This is what a glacial valley would look like. You have instead of having two very sharp ridges and like a little stream in the middle, you have two mountains over here, one over here and one over here, two mountainsides. But look at the middle. The middle is kind of shaped like a U. It's very, very broad and not sharp at all, and there's no real river running straight down the middle. This was caused by a glacier. In fact, you can see all the snow and ice in the background. You can see that a lot of it is still there, and so this area was probably caused by a glacier. This is an example of a fjord. You see a lot of these in Norway. I think one of the big things that they do in terms of tourism in Norway is they have boat tours through these fjords. Fjords are deep, steep-sided inlets in seas, kind of like valleys, but they're like flowing water that goes through the passes over here between these mountains or these hills, whatever they are. The Ice Age, so to speak, or an Ice Age, is really just an era where you have a lot of very strong glaciers. And the reason is an Ice Age is when the Earth happens to be very cold. That fluctuates every once in a while. You have areas in which the periods of time in which the Earth gets extremely cold, and that causes, of course, glaciers to expand. Naturally, you're going to have more snow, more ice, more glaciers. And that, of course, causes sea level fluctuations. The more the glaciers you have, the lower the sea level is going to be. It also causes extinction of some organisms. Even some people say that the dinosaurs were wiped out by an ice age, although that's not clear. Change in the course of some rivers. Obviously, if some features are frozen and changed, that's going to cause rivers to have to go around them or stop flowing altogether. You also have deserts. Now, deserts are obviously a lot different, but all a desert is, it's a vast, dry region that has an arid climate with very little rainfall. They don't necessarily have to be hot or cold. Most deserts are hot, but some deserts could actually be very cold. And there's not as much erosion and deposition because there's not as much water, but still, there are erosional and depositional features in desert landscapes. For example, the Grand Canyon is, of course, formed by the Colorado River, which is in Arizona, which is mostly a desert landscape. Deserts cover 30% of the Earth's surface, which is the largest of any type of biome. Again, deserts are very dry. They don't quite have the same level of features as do other areas because there's just not as much water to cause erosion. There's also, in deserts, I have my daughter in here and she's listening to me do this crash course, and so she told me to remind you that in a desert, There is cactus water inside the cactus, but cactus water is not healthy, so don't drink cactus water unless you really have to. Okay, so you have then the next other type of erosion is you have wind. Wind moves things from place to place. You know, fairly, and it's very common in the deserts where you don't have streams, you don't have running water to move things from place to place. You do have wind that moves things from place to place, and wind causes all sorts of funny types of land features in deserts. You have deflation, which is lifting and removal of loose material. The wind can only carry fine sediments. And obviously, a wind can't carry boulders, or unless it's like a tornado or something, it can't carry rocks, but it can carry sand or silt, clay, things like that that are much, much smaller. Clay is the smallest type of rock particles. Silt is next, and then sand, but it can carry and therefore make the desert, which is, if it's sandy, it can make the desert look very strange with a lot of sand dunes all over the place, all because of wind erosion. It can cause blowouts, which are shallow depressions, in other words, small holes in the ground, and desert pavement, which is a layer of loose cobbles and pebbles that are too large to be moved by the sand. In other words, if you have like a bunch of different types of rocks in there, and a wind comes and blows away all the small particles, the only thing you have left are the big particles, and so that they call that desert pavement because it's as close as you can get in a sandy desert to really have something that's kind of stable. And you can also have these wind abrasions. Okay, abrasion can actually cause some very strange features because what happens is you have the wind or other features cause rocks to be eroded and blown away and leaving strange features. I'll show you a couple of examples here. This is from the Sahara Desert. I think this is actually a natural formation. It looks like it was built by humans, but this is, I believe, natural based on wind erosion, just based on the random way the wind has blown away certain parts of the rocks and caused them to look like this. This is another bizarre example. You can see the white rocks in the front ground, the red rocks in the background, and this thing over here, which looks like the wind erosion caused a lot of the weaker materials over here to be blown out, whereas this strong rock over here was not blown out. So you can have this wind erosion in the desert causes a lot of strange features in the desert. And this is how desert pavement, which I mentioned before, forms. You have deflation, which means these sand things get blown away, and the only thing that's left are these heavy rocks, which don't get blown away, and so therefore they you just, instead of having sand, you just have a whole bunch of rocks over here. Now the other way, then this is the way desert pavement can be formed, and down here, section B, is how desert pavement can be undone, can be unformed. You have desert pavement over here, all the pebbles and cobbles, which are rocks, on top over here, but then you have other wind blowing other smaller particles towards the desert pavement, and so instead it sits there, but the rock mixes with it. In other words, if the wind blows silt and sand into the pavement, it could cause it to become back to being sandy, whereas if it blows it away from the pavement, it can cause it to become only rocky and not sandy at all. Other agents of erosion include gravity, as we discussed earlier, ice, water, these we've all discussed. The sediments, of course, could be blown by wind, and that's important for many reasons. Number one, the sediments can shape the rocks, as we saw before. Wind has a low density compared to water and ice, so it cannot move things as well as water and ice can. And wind carries sediments to large areas, not just like water can only carry sediments to the end of the water where it stops flowing, or ice to the end of the glacier, whereas wind can blow sediments pretty much anywhere. And wind can also only be an erosional force when there's not that much vegetation. Where you have soil, the soil is able to when you have plants in soil, it becomes stable to the point where soil itself cannot be blown around by normal winds. And an example, during the Dust Bowl, which was in the 1930s in the middle of the United States, there was very little vegetation because there was a drought in the Midwest and in the Great Plains. And that caused the wind to be able to transport sediments in the area, shape the landscape, and also caused enormous dust storms. Now we move to a new phase of the course, and that is plate tectonics and earthquakes. Plate tectonics is the idea that the entire Earth is sitting upon about, I think, 12 plates of land that's underneath the Earth, and these things move around, causing all sorts of problems above the surface, like volcanic eruptions, earthquakes, things like that. This is just a quick picture of the Earth and how it looks like in terms of the plates. You can see this is North America, Asia, South America, and you can see all these plates. There's the African plate, the Eurasian plate over here, North American plate, Pacific plate, and where you have the problems with plate tectonics are at the borders. Because in the middle of the plate, even with the exception of certain areas like the Hawaiian hotspot, you don't really have a lot of activity in the middle of the plates. Where you have a lot of the activity is towards the edges of the plates. And they call this whole area the Ring of Fire. And the reason why they call it the Ring of Fire is because you have all sorts of problems that happen, earthquakes, volcanoes, etc., around the edge of this plate, the Pacific plate, the American West Coast, and then you have the Pacific East Coast over here, Japan, Philippines, etc., etc. So plate tectonics really is the idea that it's more encompassing than the continental drift. I mean, we'll discuss continental drift a little later. That's the idea that the continents kind of drift apart. But, I mean, just to give you an idea over here. One second, where is this? Okay, excuse me. Yeah, okay, so like this, for example, the Mid-Atlantic Ridge, the idea is that the Americas, North and South America, drift away from Africa and Europe based on this Mid-Atlantic Ridge, which is constantly spreading the land apart as we move away from it. That's the continental drift. But plate tectonics really includes that and the idea of why you have earthquakes and volcanic eruptions and things like that. Now, the lithosphere, of course, is the crust, the uppermost mantle and the underlying crust, and that is broken into several segments called plates. The plates move very slowly. You have the Pacific plate, which is the biggest one, and I guess because it's the biggest one, at the edges you have the most momentum, and that's why the Ring of Fire is around the edge of the Pacific plate, like over here. The Ring of Fire, this is the Pacific plate. Then you have the asthenosphere is underneath the lithosphere. The asthenosphere is really the upper part of the mantle, whereas hotter and weaker than the lithosphere, and this allows for the motion. The lithosphere, which are the plates, are kind of, if you picture it like floating around on top, these plates are floating around on top of the asthenosphere, which is kind of a combination of solid and liquid rock. And because it's so hot, the rock melts and flows around, detaching the Earth's shell, namely the plates, from the layers below. The evidence for this theory, the reason why we know that this is true, is first of all you have hotspots, which are caused by rising plumes of mantle material. In other words, rising hot materials that cause volcanoes and also cause all sorts of other problems. And volcanoes form over them, like the Hawaiian island chain and Japan, plenty of other places like that. Ocean floor drilling, by drilling in the ocean floor, scientists have been able to make a determination that underneath these plates you also have the asthenosphere and you have the materials that scientists now know exist there because of drilling. And you also have this thing called paleomagnetism. Paleomagnetism is the study of the record of the Earth's magnetic fields in rocks and various other materials like clay and sand and things like that. Basically, the paleomagnetic records, in which scientists can actually look in rocks and see evidence of differences and shifts in the Earth's magnetic fields, shows that the plates have actually moved. Magnetic fields are based on the Earth's poles, the North Pole and the South Pole, and the magnetism is going to draw certain atoms and certain parts of the rocks to various parts of the rocks, and because there's evidence of different parts of the rocks being in different orientations, that indicates that these rocks have moved from place to place. I don't want to go into it too deeply, but basically just remember that paleomagnetism means the fact that scientists are able to see that different parts of the rocks indicate that you have had different magnetic fields at different components, and therefore these rocks have moved. The plates, you have plate boundaries, which are the broken segments of the lithosphere. Remember the boundary that we saw before between the different plates, between, let's say, the Pacific plate and the North American plate. These are the fault lines. These are the ones where you have the major tectonic activities, like earthquakes and volcanic eruptions. And you have, interactions among plates, of course, occur along their boundaries. That doesn't mean that it's impossible to have an earthquake or a volcano in the middle of a plate, but it does mean it's much more likely to have it at a border. Plates can be divergent, which means they are separating, like the continental drift. I'll show you a picture over here. Okay, so this, for example, is a picture of the continental drift. I'll make it a little smaller so you can see the whole diagram. Okay, well, there you go. Excuse me. Okay, anyway, let's say this is an example of a divergent boundaries. You have the asthenosphere, which is down here, the upper mantle, where you have the magma. Remember the melted rock. You have two plates that are moving apart over here. And because of that, these are divergent boundaries. The plates are moving apart, and because of that, the seafloor is spreading apart, and the continents, this continent and that continent, are getting further and further away from each other. Over here on the left side over here, you have the opposite example. You have the convergent boundaries. Convergent boundaries are where plates are moving together, they're colliding. And as you can probably imagine, this is where you have a lot of the problems. You have mountains that build. When you have the seafloor spreading, the mountains don't build. On the contrary, if anything, it gets lower over here. But if two plates collide, so you can have these actually be forced upwards, and mountains are actually built, where you have convergent plates. Then you have the transform fault boundaries, where they're pushing in other directions and pushing in different directions, and there's where you could have a lot of volcanic and earthquake activity. Okay, so divergent plates, and again, we've really kind of covered this, but let's take a look at this slide over here. Divergent plate boundaries is when they are spreading apart. They're also known as constructive margins. They're not, as opposed to destructive. Destructive is when the margins are being destroyed, whereas constructive is the distances between the continents are being increased. Two plates are moving apart, and mantle material upwells to create a new seafloor, just like we saw in this diagram over here. The two plates are moving apart, and the seafloor is spreading out. And what is this new bottom? Well, the new bottom, this magma from the asthenosphere, is going up over here, and it's filling up. And as it gets into the water, of course, it's going to refreeze, maybe become volcanic glass or some kind of rock, and that's going to cause there to be more sea floor, and the continents are going to spread further apart. Continental rift forms at the spreading centers within a continent. The example I showed you a moment ago is when it happens underneath the water, but it could also, of course, happen underneath the land, which causes the continent to become wider. And this causes volcanoes and deep valleys because the continent is spreading apart, leaving chasms in the middle, which have to be filled by rising magma. The Red Sea formed out of this rift when the Arabian Peninsula split from Africa. Let me see if I can get you a map of that area. Okay, so the Red Sea formed out of this rift when the Arabian Peninsula split from Africa. Here's for example, anyway, so here's a little map that I put over here. This is northern Africa and the Arabian Peninsula. This is North Africa with Egypt. This is the Arabian Peninsula with Saudi Arabia and Yemen and some other countries over here. And this is the Red Sea. The idea is that when the Arabian Peninsula split apart from Africa, it did so because of a continental drift, and that left the area in the middle that was a very low area, of course, and so all the land water kind of accumulated there, and that is what eventually formed the Red Sea. Also, of course, sometimes known as the Yam Suf. And so the seafloor spreading mechanism, which you see on the bottom over here, operates along the ridge system to create a new seafloor, and the typical rate of seafloor spreading in the Atlantic Ocean is 2 centimeters per year, which means right now we are getting about 2 centimeters further away from Africa and Europe every year. Now, you may think that's a good thing or a bad thing or whatever it is. I don't know if airline tickets are going to have to go up because it takes longer to fly to Europe and Africa because it's 2 centimeters a year, but we are getting a little bit further away from them every year. It takes quite a while, of course, for that to make a real difference at 2 centimeters per year. And this is an example of divergent plate boundaries. We saw a couple of these before. Partial melting, the Rift Valley spreads apart. This is the example of the mid-Atlantic ridge, where you have the upwelling of the magma, the melted rock from the asthenosphere, which goes up and forms new land in the Atlantic Ridge. And there you have Europe and Africa over here, and North America over here. And again, because of that, we're moving away from them very, very, very slowly. So that was divergent plate boundaries. Now let's look at the opposite, convergent plate boundaries. And we've got some diagrams in the slides themselves, so I don't have to find some other ones for you on the internet, but certainly if you would like to Google convergent plate boundaries, you can see lots more examples. In fact, anything for this course, by the way, that you want to just poke around on the internet a little bit, you can see lots of information for. So convergent plate boundaries are known as destructive margins because they tend to crush into each other, thereby destroying some of the elements there. Plates collide, an ocean trench forms, and the lithosphere is subducted, which means pushed down, or pushed up also, into the mantle. And here you have the oceanic or continental convergence. This is where you have a convergent plate boundary. You'd have the, for example, if the mid-Atlantic ridge were a convergent plate boundary, we'd be getting closer to Africa and Europe every year. And again, I don't know whether that would be a good thing or a bad thing, but that would be the case. It only is not the case because it's a divergent plate boundary. Okay, when you have this convergent, with the ocean into the continent, the denser continental slab sinks into the asthenosphere. Pockets of magma, we'll see all this on a diagram in a couple of moments, and pockets of magma develop and rise, and you have mountains that are formed. Examples are the Andes, the Cascades, Sierra Nevada, etc. We'll look at the bottom half of the slide in a minute, but this is an example of an oceanic continental convergence. You have the oceanic crust over here, and you have the continental lithosphere over here, and they kind of are coming together. You know, this one is moving this direction, this crust is moving in this direction, and as they come together, where you have the trench, you know, we have the convergence of the two plates in the middle. This plate goes beneath this plate, and kind of the pressure from all this added lithosphere underneath pushes this upwards. And it pushes upwards and it causes this area to become mountainous. Examples, as mentioned on the slide, include things like the Sierra Nevada mountain chain, which is on the west coast of the United States, the Andes, which is on the west coast of South America, and the Cascades, which is also on the west coast of the United States. Then you could also have convergence of plates within an ocean. Oceanic convergence. In other words, where you have two plates that come together underneath the ocean. And then you have the same basic idea. What happens is that you have the same convergence, oceanic, where you have two plates that meet in the middle over here. One goes beneath the other and forces this upward pressure because of all this new lithosphere that's underneath, forces the pressure upwards, and that could cause volcanic islands, or volcanoes in general, really undersea mountains that sometimes, really all a volcano is, it's an undersea mountain. Volcanic island is an undersea mountain that pushes its head above the sea level. That's, you know, Hawaii is mostly comprised of that. So volcanic arcs form as volcanoes emerge from the sea. Examples are the Aleutian Islands, which is off the coast of Alaska, which is on a volcanic upward, above a northward subducting Pacific plate. Let me get you a little map over here to show you what I mean as far as the Aleutians go. This is another kind of map of the world with the red lines are the borders of the plates. Here's the United States, of course, and if we focus this a little bit further over here, the Aleutians, you might not be able to see them, but they're over here, somewhere in the upper left-hand side. I'll try to make this a little bigger if it'll go a little bigger. Okay. Okay, so this is the North American plate, and of course this area is the Ring of Fire. You know, this is California, where you have the Pacific plate over here, and the Pacific plate kind of moves over here towards Asia, and right over here, off the coast of, this is Alaska, of course, and off the coast of Alaska you have the Aleutian Islands, and the Aleutian Islands are where you have convergent oceanic plates. You got one plate over here and one plate over here, and they're coming together, and that forces one plate's land going underneath the other, forces an increase or a rise in this area, and that caused the Aleutian Islands to kind of poke their head above the land, and you have these volcanic islands. Notice, of course, you don't have volcanic islands in the middle of the Atlantic, even though you have a boundary, and the reason for that is because that is a divergent boundary. They're spreading apart. If they were coming together, you'd have volcanoes formed, but because they're spreading apart, there's no pressure, and the volcanoes don't actually rise anywhere. Okay, let's move back to the slide. Okay, there we go. When subducting plates contain continental material, in other words, you have continent and continent plates. We've discussed continent and oceanic plates, oceanic and oceanic, and when two plates meet and they're actually in the middle of a continent, well, then you can produce these enormous mountains for the same reason, because and just like in the oceanic plate, you had um, when you had oceanic, you had the volcanoes building from the ground floor to poke their head above the water, whereas when you have land and land plates, the land is already there, so the mountains that start to rise from there are going to be extremely high. That's why you have, for example, the Himalayas. Back to this diagram over here. By the way, in this whole chart, you may notice the reds are the convergent, the greens are the divergent boundaries. Notice the middle Atlantic plates. The middle Atlantic plates are either divergent or transformed. That's why there's no volcanic islands in the middle of the Atlantic. But if you notice, an example of a convergent plate in the Eurasian landmass, in other words, in Europe and Asia, is over here. When you have two plates that are convergent, that are running into each other, the Indian plate and the Eurasian plate, that causes enormous mountains to form. And if you know a little bit about geography, you may know that in this area of the world is the highest mountain chain in the world, namely the Himalayas, which of course includes Mount Everest, which is the highest mountain in the world. Okay, let us go back to the slides over here. There we go. Okay, we looked at this before, convergent plate boundaries, oceanic and continental, where you have mountains on the coast of the continents. You have oceanic and oceanic, where you have volcanic islands. Here's continental and continental, like India and Eurasia, which causes big mountains to form over here, and this is the Himalayas that are formed by the continental and continental plates that come together. Then you have the transform. We've discussed the divergent and convergent, and transform fault boundaries are even more interesting. These are when plates kind of slide past one another. They don't kind of run into each other or run away from each other. They just kind of slide past each other, and as they pass each other, very often they hit each other and they cause some problems. But there's no new crust that's created or destroyed because they're not actually running into each other or running away from each other. Instead, they are just running past each other. And most join two segments of a mid-ocean ridge, but they have all different types of faults, which means breaks between the plates that cause earthquakes and cause volcanic eruptions that are caused by transform faults. Here are some examples. This is a normal fault, where you have two plates that run into each other, and because they run into each other, they kind of one goes up and one goes down. That's a normal fault. And you can imagine the stress that's caused by this, which often causes earthquakes. You have a reverse fault. Again, there's really no major differences between them, except that they are just in different directions. You have a thrust fault, where you have stress coming from this direction, stress coming from that direction, just causes this area to be thrust on top of that area. You have a strike slip fault, which causes shear, which means kind of like breaking two things by pulling them in different directions. Obviously, you can't see what I'm doing with my hands now, but you can see the diagram where you have plates pushing this landmass this way and this landmass that way. Now, you can imagine for the people sitting right over here in between the two arrows, there could be some problems there. And these kinds of faults obviously also make it more interesting or more difficult, depending on the way you look at it, to see what has happened with the rock. So, just to give you an example, let's say there were fossils that were originally over here. Let's say this stream went like this, and then kept moving. But because of this strike slip fault, because of the land moved, the stream got moved over here. So, for example, you might have civilizations or fossils where one piece is over here and one piece is all the way over here, and the reason is because they used to be right next to each other, but because the land actually moved, they're now in different places. And that's the same kind of thing with all of these. For example, over here, the theory is this, let's say, beige line, which starts over here, this beige line used to be one big long line, but because of the fault, because of the fact that one went up and one went down, they're now on different levels. So for example, you could see the same fossils over here as over here, which indicates that they were once level. They were once in the same line, then some sort of an earthquake or a stress fault or whatever it is caused them to become on different levels. That's whenever geologists are excavating and looking for different types of fossils, they have to take into account that because of plate tectonics, they could have moved, and so the fact that this layer might have the same fossils as that layer is a good indication that they probably at one time were on the same level. Okay. So movement in normal faults, what scientists will do to determine if they were once on the same level, check if the rock units on either side coordinate. If it's the same type of rock over here as over here, so it indicates that they might have been the same type, they might have been on the same level. Check with the type of fault and the angles based on relative to one another. In other words, if you see that all of them are the same distance from each other in this area, you could probably make a guess that they were all once on the same level. Check the spacing of the ditch, check the visibility of fossils, check if there are horsts, which are uplifted fault blocks which form mountains. In other words, check to see the effects of all these tectonic plates over here. This is an example of a hanging wall and a footwall. Very interesting. You can see, you can see over here in this diagram how it's obvious if you just look at it that this area, this is like a side view of a mine or some kind of a side of a mountain, and you can see that this line obviously looks the same as this line, which indicates that that they were once on the same level. And this part went up and this part went down because of some sort of a divergent, actually really probably convergent or transform plate tectonics, which was underneath. And so over here you've got areas, you have the hanging wall and the footwall, which is the idea that the walls are now in different places. One is hanging and one is higher than it used to be, one is lower than it used to be because of the movement in plate tectonics. And plate motions, plates move around, are horizontal. Obviously, they move around on the ground. The plates, they might push each other up or push each other down, but generally speaking, they're moving right and left. And of course, they require an energy source in order to move, and the way they do that is from all the heat generated by the middle of the Earth. Remember, the asthenosphere is partially liquid mantle underneath the crust, and the heat causes the plates to move around. That's basically plate tectonics. And in the next chapter, we're going to look at earthquakes, which is a result of plate tectonics. So now we're going to shift gears a little bit. We've discussed plate tectonics and plate boundaries, and the next three chapters deal with the effects of the plate tectonics and plate boundaries, namely regarding mountain building, regarding earthquakes, and regarding volcanic eruptions. Okay, so let us start with earthquakes. Earthquakes are a natural geologic phenomenon caused by sudden and rapid movement of rock underneath the particular area. And of course, they can cause tremendous destruction. They usually happen along faults, which are fractures in the earth crusts, which almost always are, not almost always, but usually are on the borders between different plates. Like, for example, the famous San Andreas Fault in California is on the border between the North American plate and the Pacific plate. As a result of these cracking and breaking, and there is violent and shaking and rupture in large fault segments can cause even larger earthquakes. Once a little bit of if it breaks, it can break further. Like a crack in a glass that could cause it to be more susceptible to other cracks. Like in a windshield, for example, if you have a little hole in the windshield, that could make it more susceptible to bigger holes. The focus of an earthquake is the origin, wherever it actually starts. Between 500 and 700 kilometers deep in the earth is usually when it happens, and the part right above where you have the actual break underneath the ground that causes the earthquake is called the epicenter. In other words, specifically which area on the surface is right above the place where the earthquake actually happened. A little diagram over here. You have the buildup of strain because of some kind of a fault, and you have some sort of a strain that breaks the ground above it. The focus is where it actually happens. The land above the focus is the epicenter, and of course the earthquake will affect this whole area. The further away from the epicenter it is, the less affected it will be. Seismology is the study of earthquake waves. In fact, seismology in general, seismologists are people who study earthquakes. And the way you measure an earthquake is with a seismograph. Seismology is same root of the word, obviously. It records earthquake waves, and the record is called a seismogram. Anything to do with seismo has to do with earthquakes. You have surface waves, which is motion that's on the Earth's surface or near the Earth's surface, and body waves, which go through the Earth's interior. And the two types of waves are P waves and S waves. P waves are primary waves, and S waves are secondary waves. Now, both of them can cause destruction, but of course the P waves, which are directly from the earthquake, which are caused directly by the earthquake, are more destructive and more intense than secondary waves, where you have a primary wave, and the primary wave causes the earth along which it's running to shake, and that causes secondary kind of ripple waves. If you throw a rock into the water, and you get the primary splash, and then you get a bunch of ripples on the outside. The secondary waves are more like the ripples. So the P waves travel through any kind, travel through solids, liquids, or gases. They have compressional motion. They push or pull the earth that is along its way, and it has the greatest speed of all earthquake waves. S waves only travel through solids. They cannot travel through liquids. That's actually one of the reasons for that the scientists were able to figure out that the center of the Earth is, or I'm sorry, the outer core really, is liquid, because of the fact that earthquakes, when you measure them, don't come through. P waves do come through on the other side of the Earth, but S waves don't. I mean, just to show you a little bit of a diagram over here, if this is the center of the earthquake, let me make this a little smaller so you can see the whole diagram here. Let me give you a different diagram. It looks a little easier to see. Over here you have the epicenter, or the focus. The epicenter would be on the land, focus a little bit beneath the land. But the P waves, if you look over here on this side of the Earth, where the waves don't have to go through the outer core, you feel both the P waves and the S waves. On the other side of the Earth, where the waves have to go through the core, through the outer core, which is liquid, you can only feel the P waves and not the S waves. Now, because of the way earthquake bends, there are also these earthquake waves bend. There are also these shadow zones where you don't feel any of them. Now, look, obviously, you're not really going to be able to actually feel an earthquake on the other side of the world, because once it gets all the way to here, it's going to be so weak that you're not going to be able to feel it. But seismographs can pick up waves. If there's an earthquake in Australia, waves in the United States, our seismographs can pick it up, even though obviously we're not going to be able to feel it. But this is one way that they deduced that the outer core is liquid, because on this side of the Earth, they saw that the seismographs, when there was an earthquake over here, on this side, they were only reading P waves, not S waves. So they figured out that there must be some liquid over here in the middle, in the core of the Earth, that was blocking out the S waves, because S waves do not travel through liquid, they only travel through solid. Okay, how do you measure earthquake waves? Well, you measure in intensity, which is the degree of an earthquake at a given scale based on the amount of damage. You can also measure it based on magnitude, which is not based on how much damage it causes, but based on the measurement of the ground motion. How much did the ground actually move? And the most famous way that earthquakes are measured is of course, Richter scale. The Richter scale is based on the amplitude of the largest seismic waves recorded on a seismogram, obviously near the epicenter of the earthquake. It doesn't measure the extent of the building damage. There's another scale, I think, called the Mercalli scale, which measures the building, the amount of actual damage caused. But the Richter scale measures the magnitude of the earthquake. How strong was the earthquake in itself? Now, the Richter scale is what is known as a logarithmic scale, which means that a tenfold increase corresponds to each 1 point. An earthquake with a 4 is 10 times greater than an earthquake with a 3. Otherwise, the scale would just get too big and it wouldn't make any sense. So if you hear one earthquake is a 6 and the other earthquake is a 7, it sounds like they're pretty close, but actually the 7 is 10 times greater than the 6, and an 8 would be 100 times greater than a 6. So each unit of Richter magnitude has a roughly 32-fold increase. So a 6.5 releases 32 times more energy. It's 10 times as great a magnitude, but it releases 32 times more energy. So you could imagine that small differences in the Richter scale actually can translate to enormous differences in the amount of damage caused. Now, I'm not going to go into all the nitty-gritty of measuring earthquake intensities. That's a little bit beyond the scope of what we're covering. But this is actually something that's important to know a little bit about, and that is the fact that you can infer the epicenter of an earthquake based on how long it took to get there. Earthquakes uniformly take the same amount of time to move from place to place. From the epicenter, you can see the P waves move a lot faster. The S waves also move, of course. After 1 minute, you can see the P wave will have moved about, this is 1,000 kilometers, each one of these. So after 1 minute, the P waves will have moved about 400 kilometers, and the S waves only about 200. Each one is 1,000. 1,000, 2,000, 3,000, 4,000, 5,000. Let's say after 10 minutes of the earthquake happening, well, the S waves have moved about 3,000 kilometers, whereas the P waves have moved almost 7,000 kilometers. This is a chart that just indicates how fast P waves and S waves move, and you can see P waves take a lot less time to get places, and so P waves are a lot faster. One thing you can do is in helping to determine the way they determine where the epicenter is. Now, obviously, when an earthquake happens, there's no little sign that pops up in the ground and says, "Here, I'm the epicenter." The only way you can really determine where the epicenter of an earthquake is if you have seismographs in different areas, and there are seismographs that are always on, like in University of California. Berkeley probably has a seismograph, and many places all around the world have these different seismographs. And if you can determine how far each seismograph is from the center of the earthquake, you can figure out where the earthquake started. Basically, you can triangulate. If you have 3 seismographs and each one tells you how far it is away, then you can put somewhere in the middle. If this were a map, if there was a point over here which said that the earthquake was, well, it's a bad example. Okay, I think I got some better examples over here. There we go. All right. Let's say you have 3 seismographs. You have a seismograph at station 1, a seismograph at station 2, and a seismograph at station 3. I'm sorry. So you have now. Let's say, for example, based on this chart, this chart can help you tell how far the seismograph was away. So because for example, let's say you have a seismograph, and the seismograph tells you that the P waves and S waves arrived 5 minutes apart. Now, obviously, you don't know exactly how long it's been. When the seismograph measures it, you don't know when the earthquake actually happened. All it tells you is that the P waves arrived at 7 o'clock and the S waves arrived at 7:05. Well, they're 5 minutes apart, so what you can do is you can look at this chart over here. You can look at this diagram and see, okay, where are the P and S waves 5 minutes apart? And I'm just estimating. It looks like they're 5 minutes apart at about roughly 3,200 miles of somewhere around here is where they're 5 minutes apart. From 6 to 11, something like this. So let's say they're 5 minutes apart, and you can say, okay, well, if they're 5 minutes apart, that means the epicenter must be about 3,200 kilometers away. And you can do more precise measurements, but now, if they're 3,200 kilometers away, that means that the earthquake's epicenter has to have been somewhere exactly 3,200 miles away. So in spot number 1, well, this is, instead of 3,200, the 3 examples they give you are 800, 500, and 1,200. In other words, from seismograph 1, you figured out that based on the time difference between the P and the S waves, you figured out that the epicenter must be 800 kilometers away, which means it could be anywhere on the blue line. The blue line is a circle. That's all the points are exactly 800 kilometers away from station 1. Then you have station 2, which is in a different place, which measured 1,200 kilometers away. Then you have station 3, which is in a different place, that measured 500 kilometers away. Now, if you draw all the circles, in other words, all the possible distances between all the possible points of the epicenter, which is on the edge of all the circles, wherever all three circles meet, that has to have been the epicenter. That's how they triangulate. Triangulate meaning with 3 points where the epicenter of an earthquake is. Station 1 measured 800 kilometers apart, so it could be anywhere on the blue line. Station 2 measured 1,200 kilometers away, the epicenter, so it could be anywhere on the red line. Station 3 measured 500, so it could be anywhere on the black line. And where all three circles meet, where all three circles meet, that must be the epicenter. So that's how they figure out where the epicenter of an earthquake is using a chart like this. Now this is a similar example. This is an actual earthquake example. This I actually picked off the internet, and this is recorded by Science Horizons, a seismograph at Melbourne, Florida. There was some kind of so if you see over here, the P waves were picked up and over here, and the S waves over here, which means the P waves were picked up at 14:57 and 30 seconds, and the S waves look like they were picked up at about a little after 14:58. Well, let's zoom in a little bit over here. It's hard to read this in the lower left-hand corner, but you'll have to trust me that it says 14:57:30. So the P wave hit over here. This is 14:58. This is 14:58:30. Again, that means P at 2:58 p.m. This is 2:59. So 2:57:30, 2:58, 2:58:30, 2:59. So you can see the P waves hit at approximately 2:57 and 35 seconds about. If this is 2:57:30 and this is 2:58, so this is about 2:57:5. Then the S waves hit over here, which is about 2:58 and 35 seconds. So it looks like about 1 minute later. So in this particular example, the P waves and the S waves appear to have hit almost exactly a minute apart. Each one of these lines is 30 seconds, these gray lines, so they hit about a minute apart. Once you know that they've hit about a minute apart, you can then go back to this chart and figure out how far away is the epicenter, because where are they a minute apart? Now it looks like they're a minute apart at about 600 kilometers, it looks like. And I'm going to zoom in a little bit over here. Let's see. Okay, there we go. I'm just looking at the lower left-hand corner. This is the same diagram, but a little bit more zoomed in. So we can see where are they about a minute apart. Now remember, this is time over here. So we can see over here, it looks like they're a minute apart right over here. See, the P waves arrive after 1 minute and 20 seconds, and the S waves at about 2 minutes and 40, so that's not really a minute apart. It's somewhere over here. Somewhere in this area over here, 500-600 kilometers. But if we, in other words, if we see where they arrive a minute apart, and then we look down to see how far has it traveled, it looks like it's somewhere around 500 or 600 kilometers away. So based on this chart, over here where they moved a minute apart, you can infer that the epicenter of the earthquake is somewhere around 500 or 600 kilometers away. All right, effects of the earthquakes. For effects of earthquakes, there's going to be a lot of variables and a lot of things that it depends on, including location. Where did the earthquake happen? Obviously, if it happens in the middle of Los Angeles, it's going to be a lot more problematic than if it happens in the middle of Death Valley. Magnitude. Obviously, the higher the magnitude, the more shaking you're going to have. You're going to have the more shaking over a larger area and, of course, cause a lot more damage. Depth beneath the Earth's surface. The greater the depth, the less the surface will feel. The more destructive, the closer to the surface that the earthquake happens, the more destructive it will be. The type of fault, is it a fault that has a lot of, that's very broad and has a lot of material, or is it a fault that's relatively small? Mechanism of the fault rupture. Was it just a transform boundary where they kind of brushed each other, or was it where they ran into each other? Those are factors. The direction of the rupture. These are all things that obviously make a determination of how devastating an earthquake will be. Also, the soils. Soils in the area will determine how fast they move and how quickly they dissipate. The thicker the soil, obviously, when you're talking about the mantle or the asthenosphere under the Earth, it's pretty constant. That's why they can be measured by seismographs relatively easily in terms of how fast they move. They move pretty consistently, but in terms of moving along the ground itself, if the soil is thick, it may blunt some of the impact. Where if it's rocky and there's not much water, it will move a lot easier through. Softer soils are usually less safe than firm ground because the ground turns to mush and loses its strength to support structures. So if you have a city that's built on soil type rock, it's a lot more problematic for earthquakes. In terms of human effects, obviously the more populated the area of the epicenter is, common sense, the greater the population devastation can be. If the epicenter is in the middle of a city, there could be much greater than if the problems will be much greater than if the epicenter was under a mountain where nobody lives. The intensity, the greatest damage is usually near the epicenter. As you go further and further away from the epicenter, the damage will usually be a little bit less. But it also depends on, in areas of poor soil, even if it's further away from the epicenter, it's more likely to shake and ruin the soil and cause things that are built in the soil to fall. And so even if you have an area with soil that's built on soil further away from the epicenter than that's built on rock, the area built on soil might be more devastated. And also, the more prepared for an earthquake you are, the less you may suffer the damage. California's earthquakes, because California is on the San Andreas Fault and is susceptible to earthquakes and has earthquakes, California's building and structures are built specifically to withstand earthquake activity. The active San Andreas Fault is underneath the most populated areas in California, and so danger could spread to a large area, whereas other areas where you've had major earthquakes, places like Iran, places like in Asia and South America, where you've had major earthquakes where the buildings haven't been built with a code that was designed to withstand earthquakes, it could be a lot worse. Also, of course, if you have surprise earthquakes in areas where there just isn't that much expectation of an earthquake, the buildings might not be built to withstand earthquakes. There was an earthquake a few years ago that was in Virginia that I felt it. So it could be felt in the New York area as well. Thankfully, it wasn't such a strong earthquake, so it didn't cause a tremendous amount of devastation, but certainly it's the sort of thing that we don't really expect in this area. So earthquakes of similar magnitudes don't necessarily mean equal damage because of these factors. You could have a 7 on the Richter scale in the middle of the desert, might not hurt anybody. Even in the city, if the city is prepared for it, it might not be so bad. Whereas a 7 earthquake in the middle of a slum in Asia where there are millions of people there and the buildings are not built properly, or in Haiti or something, it could cause major problems. Earthquakes can also cause tsunamis when you have underwater earthquakes, and the underwater earthquakes are where the ground and the water underneath the ocean shakes, and they could cause enormous waves, huge waves that are many miles or even kilometers. The waves are only a few feet high, but they're very strong and they travel hundreds of miles. And when they wash into the land, whenever they finally break into the land, they could cause tremendous devastation and kill thousands of people. I mean, a few years ago there were tsunamis in Asia which killed tens of thousands or even hundreds of thousands of people because huge waves buried huge coastal cities all around the southern Pacific Rim. Earthquake damage, of course, also varies from earthquake to earthquake. Factors affecting, you see some repetition in these slides over here. Design of structures, nature of the surface material, how much the vibrations are, and how long the vibrations actually happen. All these factors are important. And finally, we have a quick discussion of the Earth's interior. Most of the knowledge of the Earth's interior comes from data drawn from seismic waves. Seismographs that read earthquakes can infer, as we saw before in that diagram, what the nature of the Earth is. In other words, if scientists see that the earthquake shows up in a certain region in a certain form, it can say, well, the ground must have been a certain type of ground. The mantle must have had a certain type of composition in order to allow it to get there. The Earth's crust is the thinnest of the major subdivisions. The continental rocks are different than the oceanic rocks. Again, that's just the rocks that the Earth is sitting on, the ground is sitting on. The Earth's core is dense and consists of iron. We saw this before already, but just they put it in this chapter also because it's inferred from earthquake data. You have the crust on top, either oceanic crust over here, continental crust over here. Then underneath you have the asthenosphere, which is the top of the mantle. Then you have the lower mantle. Then you have the outer core, which is liquid iron and nickel, and the inner core, which is solid iron or nickel. And that is the Earth's layer and how it is inferred from earthquakes. The next two chapters on volcanoes and mountain building are all based on things that we've already learned, so hopefully they can go relatively quickly. Volcanoes are based on igneous activity. Remember, igneous is when igneous rocks are formed when lava or magma melt, or freeze, excuse me. Melted rock refreezes into different types of rocks, into igneous rocks, and the way in which lava spews over the surface of the Earth is typically through a volcano. A volcano is a mountain formed of lava or pyroclastic materials, which means melted rock. That's really what lava means over here. When it's underneath the ground, when melted rock is deep underneath the ground and not on the surface, it's called magma. It's the same thing. Lava and magma are the same idea, but magma is when it's deep beneath the surface of the Earth. When it comes on top of the surface of the Earth, it is then known as lava. In fact, mountains that are built from lava, the magma spurts out into the ocean or onto the land, and eventually refreezes into rock, and this rock forms a mountain. Many times, obviously, if it happens many times, the mountain could get higher and higher. That is then called a volcano. Volcano doesn't necessarily have to be high. Volcano theoretically doesn't even have to be much of a mountain at all. Any place in which lava can spew over the surface of the Earth is called a volcano. There are volcanoes that erupt explosively. Lots of lava comes through at once and tremendous amount of heat and destroys pretty much anything that is above it. That happened in Mount St. Helens in 1981 in Washington State. You can actually go to St. Helens today, and you can see the complete devastation that was wrought by the volcanic eruption that happened then. Then there are more quiet eruptions in which the lava comes out much more slowly and with much less damage. The factors that determine what kind of extrusion means when the lava or magma comes out from beneath the surface of the Earth, ejection of lava from the volcano, depends on the composition. What's the magma made from? How pressurized is it? What's its temperature? The hotter the temperature, the more likely it is to explode violently over the surface of the Earth, and the amount of dissolved gases the magma contains. The more gases that it has, the more explosive that it will be. Another important aspect of magma is its viscosity. Viscosity means its mobility. In other words, the amount that it can flow. Sometimes you'll hear people say that this motor oil is the best motor oil because it has the highest viscosity. Viscosity means the ability of it to flow, which is very important when you're talking about motor oil, because that keeps the engine from gunk from building up and whatnot. So this is also a measure of resistance to flow. The more sticky it is, the more resistance it is to flowing. It's similar to more viscous corn syrup than less viscous water. Corn syrup flows a lot less than, of course, water does. The more viscous the magma is, the greater the eruption, because the more it can flow, the more it can slide out of the Earth, the more you're going to have smaller, more frequent eruptions of lava, which are going to be less violent, whereas if it builds and builds and builds and builds and builds, eventually you're going to have a massive volcanic eruption like they had in the Philippines a few years ago, like they had in Mount St. Helens, etc. Other things that affect viscosity include the temperature. Hotter magma are less viscous, which means that the hotter it is, the more liquidy it's going to be, and so therefore the more it's going to flow. Viscosity actually means the inability to flow. I might have misstated that before, but viscosity, the more viscous it is, the less it's gonna flow freely. Its composition, how much. Remember, silica is the same word as silicate. It has silicon and oxygen. The higher silica, more silicon and oxygen, the more quartz-like material it has in it, the higher its viscosity. Whereas lower silica is going to be more fluid. It's going to flow much more easily. So again, the higher viscosity, the less it's going to flow, and therefore the more it's going to build up, and the more dangerous its eventual volcanic eruption is going to be. And also dissolved gases, mainly water and carbon dioxide. Gases expand near the surface because there's less pressure. In other words, deep, deep beneath the surface of the magma, the gas is going to be very, very compressed by lots of rock on top of it. Nearer to the surface, there's less pressure on it. Where are volcanoes located? Well, volcanoes are located in areas where you have high tectonic activity. Most are located near the ocean's basins. They're located in the Ring of Fire, which means in the edge of the Pacific Plate, the edge of the Pacific Ocean in all these areas. So the ocean basement is rimmed by the most subduction zones, which means plates that converge on each other and smash into each other. Volcanoes like Mount Rainier, Mount St. Helens, Mauna Loa, which was in the Philippines, I think it erupted in, 1992 or 1993. There are other types of active volcanoes like the Hawaiian Islands, the Galapagos Island, Easter Island, All of these are actually not among the these ones are in the middle of the ocean. The third group of volcanoes are those that are in the continental interiors that are not near the ocean. So there's three types. There's one that's near the coast, near the plate borders, like St. Helens, which is in Washington State, right near the Pacific Ocean. Mount Rainier, also in Washington State, near the Pacific Ocean. Other groups are in the ocean itself, and the third are volcanoes that are in the middle of the continent. That's also possible. Again, it really depends on the convergent plates that are beneath it more than it does whether there happens to be ocean or land above it. And Chapter 10 is about mountain building and crustal deformation. We discussed already before briefly how you have convergent zones where you have two plates, one coming from this side and one coming from that side, and they run into each other, and one kind of goes beneath the other and forces the other land to rise. That's how mountains, and especially volcanic mountains, are built, and now we're going to learn a little bit more about it. The orogenesis is just a word. Genesis, by the way, always means the beginning of something. And orogenesis just means the beginning of mountains. This refers to the process that collectively produce a mountain belt. If you notice mountain chains in general, you don't usually have individual mountains. Rather, you have belts of mountains or chains of mountains. And the reason is because the plates are huge, and when the plates run into each other and one runs beneath the other, they tend to have an entire belt of an area, a huge long thing running maybe thousands of miles, rise rather than just one individual mountain pop up. If you look at a map of the United States, for example, you have this whole area with no mountains at all. In the east, you have the Appalachian chain, which is again kind of a flat belt of a mountain chain, which starts down here in Tennessee and Kentucky and rises all the way up into the northeast. What we call mountains, the Catskills, the Adirondacks, are really just part of the Appalachian chain. And then you look at the west. In the west, you have a few also mountain ranges, not individual mountains, but you have the Rocky Mountains, which is over here. You have the Sierra Nevada Mountains, which is over here. You have the Cascades, which is along the coast, right over here. So you have mountain chains or mountain ranges, because they converge they form where you have the convergent plate boundaries, and the plates are very, very long. When they hit each other, they hit each other on a 1,000-mile front or a 2,000-mile front or whatever it is. You also have a volcanic island arc where the lithosphere, name again, subducts, which means goes underneath an oceanic plate, like we saw the Aleutian Islands before, is an example of a volcanic island arc, but it's the same basic idea. Just like the Rocky Mountains or the Sierra Nevadas are where two plates hit each other and it causes a very, very long front of a mountain range, the same thing is true when you do it underwater, and when you do it underwater, you get a series of volcanic islands like the Aleutians. Where you have this happen on the coast, like in the case of the Sierra Nevada mountains and the Cascades. The Cascades are up here, Sierra Nevadas are like over here. That's what's called Andean type mountain building. And the reason why it's called Andean type mountain building is because one of the most famous examples are the Andes. The Andes happen to be on the west coast of South America. Here's an example. Here's South America. This is Brazil. Argentina's down here, where you can't really see. But on the west coast of the entire continent, of the entire South America, you have a huge mountain range throughout most of the country of Chile, which is over here, called the Andes. And so the reason why this is called Andean mountain building is because it takes its name from the Andes. And the Andes are where you have an oceanic crust and a continental crust converge. Now, you may recall from when we saw this before, but you have one big plate over here, and then you have the Pacific plate over here, and this is a convergent boundary, this yellow line where the Andes are formed is a convergent boundary. And so where you have a continental plate over here and an oceanic plate over here, and they converge, they come together, causing an enormous mountain chain to build, that is sometimes referred to as Andean-type mountain building. An example, the Andes Mountains, which we just looked at. It occurs along a passive continental margin between the continent and the oceanic plate. And it happens prior to the formation of a subduction zone, before the plates actually run underneath each other. That's the first stage. The second stage is forces that drive the plate tectonics cause a subduction zone. In other words, one of the plates goes underneath the other one, causing the other one to rise high above. And this causes an accretionary wedge. What happens with an accretionary wedge is that when one of the plates are moving under the other plate, it takes together with it all of the sediments, all the rocks and all sorts of other materials from, let's say, from an ocean floor, and pushes it underneath the other plate. And once that happens, when it forces, as the plates go one on top of the other, it causes it to rise, and all this stuff, these new sediments become part of the mountain range because it's all on top of another. Think of the accumulation of sediments in a small tectonic blocks that form materials from a descending lithospheric plate, and it's piled toward the leeward side of the trench. Now, in English, you probably didn't understand a word of that, so I'll try to show you a diagram over here, show you a picture to show you how it works. Let's say this is a subducting plate. Again, we're talking about Andean mountain building, so you have, I think we looked at this diagram before actually, in a different context. But here are the Andes, or some other mountain chain that's being built. But as this, you have the oceanic crust plate over here, and you have the continental plate over here. Let me move this a little further over. So the continental plate here and the oceanic plate over here. As this moves along, and as all the sediments from the bottom of the ocean over here gets buried in this area, and as this moves over, it drags all of these sediments and all this junk along with it underneath here, and so when this forces up the continental material, it has all this extra stuff, and that could cause very high mountains to form because of all the junk that was driven underneath the land by the subducting plate. Okay, so this could cause the wedge large enough to stand above sea level, and we see that's an example of why high mountains can form in these areas. You also have fault blocks, the Sierra Nevada mountain chain, et cetera, et cetera. These were lifted by faulting, just like we saw before. Again, there's no real difference between this kind of mountain building and the ones that we've seen before. Okay, here's another example of an Andean-type mountain building. You have the two plates. You have the oceanic plate over here, and you have the continental plate over here. And you have the materials in the ground that is driven down by the subducting plate, the subducting lithosphere. And that causes all this material to be forced upward until you have a mountain chain over here. And that's really the section of the course that regards geology. Next, we are going to move into meteorology. We're going to move into weather and the atmosphere. I think it'll be a little bit less dense, and also I think it's very particularly useful and interesting. So let us get to that one.